Hi there, thanks for joining us on yet another episode of Space Nuts. My name is Andrew Dunkley, your host, and it's good to have your company again. Thanks for joining us. Coming up, we'll be looking at an old chestnut, the expansion speed of the universe. The theory is again under the spotlight due to, for a change, non-conflicting evidence. So we'll talk about that. And a giant volcano has been discovered and it was hiding in plain sight. Guess where? Yeah, you're right. We'll be talking about that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us to explore all of that is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Good to see your smiling face again. You look a bit healthier than you did last time I saw you.
Yeah, improving. I generally don't suffer jet lag for very long, but this time it's really hit me hard. Yeah, and I think it's got everything to do with the fact that I managed to sleep on the flight home, which was bad because we got home at 8 o'clock in the evening. So, and I calculate I probably slept 7 hours on the plane because it left in the evening.
That's pretty good. Yeah.
Yeah, I know. And then when we got back, of course, I didn't really feel that sleepy. So, and it's taken me a long time to adjust, but I'm starting to get it all back, which is good. Getting over the illness that came with it. I do not recommend having a heavy cold or COVID or whatever it is I had in conjunction with jet lag. They do not like each other, and they fight tooth and nail. So, yeah, not a fun combination, but I'm sure it's not uncommon in this day and age. But we're getting through it. It's been a bit of a long haul. Boom, boom. How are you?
Yes.
How are things?
Fine, thanks. A bit chaotic due to my upcoming trip as well. So, but we'll be fine. We'll be fine.
Yeah,
hopefully.
Well, can't wait to talk to you about that. In fact, when this episode is out, it's probably around the same time as you'll be at the event that you're attending. So, that'll be good. Fred, let's get stuck into it. We've got a couple of really amazing topics to talk about, things we've talked about before, one of which we've talked about many times before, the other we haven't because it's only just been discovered. We'll get to that shortly, but let's talk about this situation with the expansion speed of the universe. We get a lot of questions from the audience about it. It's in the news again because an old theory has sort of been confirmed by more evidence from a new source, and that's that's great, but it's also got people saying, well, hang on a minute, this can't work, it doesn't add up, there's still a hole in the information and we can't figure it out. It's really quite an intriguing scenario and a real head scratcher.
And there's a lot of scratched heads in the astronomical community, exactly as you've suggested there, Andrew. So, what are we talking about? Let's, as they say on the radio, let's unpick the story a bit. We have a number of different ways of measuring the expansion of the universe, and what we're talking about here, Andrew, is the expansion of the universe now. In other words, we're not talking about, back in the day or back in the origins of the universe. We're talking about the expansion speed now. And astronomers have got a slightly curious way of expressing that. It is because the bottom line is, with an expanding universe, the further away you look, the faster something is receding from you. And that is just standard geometry. The further away you look, the faster it's moving. That was Hubble's discovery back in 1929. And the speed that things are moving away from us are measured in units of kilometers per second. That's the speed. We can understand that. But it's kilometers per second per megaparsec. In other words, well, let me just tell you what a megaparsec is. It's a million parsecs. 1 parsec is 3.26 light years. So a megaparsec is 3.26 million light years. To use the numbers that we're more commonly familiar with. Astronomers use parsecs and megaparsecs because that's the measurable quantity. You can't measure a light year, but we can turn the measured quantity very easily into a light year, which actually is a nicer way of expressing things. It's one most people can get their heads around, the distance light travels in 1 year. So the value that the Hubble telescope arrived at, and remember, when the Hubble telescope was launched back in 1990, one of its main aims, the main aim of the mission, was to measure the expansion velocity of the universe. In other words, measure the Hubble constant. And that was because at that time, and I remember this very clearly, there was huge disparity in different camps on what this constant was, ranging from 50 kilometers per second to megaparsec per megaparsec to 100 kilometers per second per megaparsec. In other words, they differed by a factor of two. Two groups of astronomers who were both convinced they were right, but their values were so far apart, they could never be reconciled. And it turned out when the Hubble telescope did its work and measured that expansion, the value was almost exactly the average of those two, 50 and 100. It's 73 kilometers per second per megaparsec. And that is now the accepted value coming from the Hubble Space Telescope. However, the problem is that there are other ways of measuring the Hubble constant, and they involve looking back at the cosmic microwave background radiation, which is, as you know, we've talked about it many times before. It means we're looking so far in space that we're looking so far back in time that we're seeing back to a time when the universe was still luminous. We're seeing effectively the last vestiges of the flash of the Big Bang, and in fact we're looking back to within about 380,000 years of the Big Bang. Now that cosmic microwave background radiation, I call it the cosmic wallpaper because it's behind everything else that we see in the universe, but also because it's got patterns on it, like old-fashioned wallpaper often did, and those patterns are caused by actually acoustic oscillations within the fireball of the universe. So there are slightly warmer and slightly cooler zones on that cosmic microwave background radiation. And by studying those, you can arrive at a value of the Hubble constant. The problem is it doesn't agree with the Hubble, the method that the Hubble telescope used, which is to look at, I didn't say this, it's to look at a particular type of variable star, Cepheid variable stars, which have a known brightness. They are what we call standard candles. So that gives you, the Hubble telescope observations gives you 73 kilometers per second per megaparsec. But looking at the cosmic microwave background radiation, you get 67 kilometers per second per megaparsec, which is, it's sort of, almost a 10% difference. Not quite, but getting on that way. So that is what we call the Hubble tension. That is what worries people, that we are getting a different answer. And in a way, back in 1990, when the Hubble telescope was launched, people would have just ignored that difference because they would have said, well, that's near enough to for us to know what's going on. But today we're in an era which my PhD supervisor, Professor Malcolm Longair, once described as an era of precision cosmology. We are in an era of precision cosmology. In other words, we can measure these parameters much more accurately than we ever could before. And so this difference from the cosmic microwave background radiation, 67 kilometers per second per megaparsec, to the Hubble telescope's 73 kilometers per second per megaparsec, that is a problem. And it's something that we would like to understand, and we don't. So that's the backstory. Now enter the James Webb Space Telescope, the JWST, which
I'm sure many people were hoping would absolutely solve this problem and say, okay, this is exactly what's happening, and that didn't happen.
No, it didn't. What the James Webb Space Telescope has done is confirm the Hubble telescope value. They've looked at the same stars. They've looked with a much bigger telescope than the Hubble, penetrated much further into space because it's got a bigger mirror. And what they get is the same answer. And by the way, this is research led by Adam Rees of Johns Hopkins University. He was one of the 3 people who got the Nobel Prize for the discovery of the accelerated expansion of the universe. So he's not somebody, that you can ignore. His research is top-ranked research done on a top-ranked telescope, and it basically gives the same answer. In fact, not basically, it gives exactly the same answer, 73 kilometers per second per megaparsec, as the Hubble telescope did. And what they're doing is they're using a combination of these Cepheid variable stars and another distance indicator, which we call type 1a supernovae. These are exploding stars that always wind up with the same maximum brightness. So you could describe these types of stars as standard candles because they are luminous and they have a standard brightness. And you can describe the work done on the cosmic microwave background radiation as being the standard rulers, because you're measuring the separation of hot and cold spots on the cosmic microwave background radiation glow itself, and standard. So we describe those as standard rulers because they are telling we kind of know what those separations ought to be, and we can measure how they look. Somebody has suggested the possibility of a technique called standard sirens. And I haven't come across that term before, but I like it very much, where you can use gravitational waves. So using gravitational waves, and I guess the standard sirens is because they're effectively the same frequency range as audio waves. Standard sirens from gravitational waves might one day help to resolve this problem. But at the moment, we simply don't have accurate enough values. The error bars are too big, so we don't have accurate enough values to use the standard siren method to resolve the issue. But that might be the way it goes. At the moment, the Hubble tension remains with us, and we don't know what the expansion rate of the universe is.
Well, yeah, we know 2 numbers.
We know 2 numbers, but we don't know which one's right.
Yeah. So James Webb confirming the data from Hubble does not absolutely guarantee that number is right. The other number is 67 kilometers per megaparsec, which was based on the baryon acoustic oscillation theory or evidence. The difference is 6. Which is a big number in an era, as you said, where accuracy is becoming the norm. I could throw you on the spot here, Fred. Do you have any theories about what the difference might be? Why it exists? I mean, it's probably a dumb question to ask because no one knows the answer.
No, but one possible answer is really intriguing. That. There are phenomena at play that we don't yet understand or know about. New physics. The universe might not be as we think it is. We've got this very neat and tidy view of the universe. And that's a fairly ambitious thing when you think that you're talking about a whole universe. We might have neglected something that we have not yet discovered. Certainly our basic theories are all correct. Relativity works perfectly. Quantum theory works perfectly. And they themselves are not reconcilable. So that's another tension as well. But the Hubble tension may come down to something that we just have not discovered yet. And when we do, it might change our view of the universe markedly. New physics, if I can put it that way, physics that we don't yet understand, could open the door to all kinds of different things, extra dimensions, all sorts of things of that sort. So it's very exciting in its own way, this Hubble tension. People are going to keep chipping away at it until we get an answer. And somebody will come along with a theory that says, what if there was a fifth dimension and it did this to the other four. Yeah, that could be the answer, but we don't know yet.
Look, let me throw a curveball at you just because it popped into my head. Yeah, it is a curveball. But if we do find some new piece of information that answers the question, could that then put a dent in Einstein's theory of relativity? Because he always thought he was wrong. He always wanted to be proven. Yeah. So and yet, as yet, all tests have proven him right.
Yes, with a very high degree of precision. So what it might show is that Einstein's relativity is only part of the story. In a similar way to Einstein's theory of relativity, the general theory, which is all about gravity, that showed that Newton's theory was only part of the story. Newton's theory works really, really well until you get into high gravitational fields, and it doesn't work at all. But Newton didn't know about high gravitational fields, and it works really well. But it's well enough that it is telling us part of the story, but not the complete story. Maybe the same is true with general relativity, with Einstein's theory, that it's telling us part of the story, but not the complete thing.
One more point with Hubble tension. Somebody is going to ask the question as to whether or not the influence could be dark energy or dark matter or both. Is that a possibility?
Well, they're all taken into account in these calculations. You know, we do know about them, but they're all taken into account. I'm sorry.
That's somebody with the answer.
I hope it is. Yeah, don't know where my phone's gone. It's all right. They've stopped ringing anyway. So.
Fair enough. All right. Well, it's one of those questions that will remain mysterious until somebody somewhere who will probably win a Nobel Prize comes up with that light bulb moment, possibly a standard candle moment. Boom, boom. We'll have to wait and see. With the cosmic microwave background radiation diminishing, I assume it's diminishing, will there come a time where we can't rely on that anymore?
It's diminishing in the sense that that radiation that we see, that sort of wall of radiation, which is what it is, that is actually moving away from us at the speed of light. But over time, those patterns, what we call the baryonic acoustic oscillations, which you refer to, the patterns in the wallpaper, they will change. But we're talking about millions, if not billions, of years.
So we've got a bit of time to solve this.
Yeah, we've got time to work on it, Andrew.
All right, sounds good.
Goodness knows we need it.
Yes. Sometimes we do.
Yeah.
If you would like to read up on that story, it is a really fascinating read. It's sciencealert.com. This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Now, Fred, to a discovery that has been confirmed, and there will be no doubt, and that is a major announcement at the 55th Lunar and Planetary Science Conference in Texas the other day, that they have discovered a new volcano beyond Earth, and not surprisingly, it's on Mars. It's a monster, and it's been in our face all this time. We just haven't really noticed it. Probably due to weathering or erosion or whatever you want to call it. But yes, a new, well, it's not new, but it's new to us, new volcano on Mars.
We know of several volcanoes on Mars, and including the highest mountain in the solar system, Olympus Mons, 23 kilometers high above the plains of Mars, a huge volcano. This new discovery, which I might just mention at the beginning of our chat about it, is by Dr. Pascal Lee, who's a planetary scientist with the SETI Institute and also the Mars Institute, based at NASA Ames, and he is the lead author of the study. So what Pascal and his colleagues have done is looked at many what you might call aerial photos of Mars the imagery taken from orbiting spacecraft, of which there have been many since Mariner 9 in 1971, and combined it with the radar measurements, basically measurements of the height of the features on Mars's surface, which have come from other spacecraft. Mars Express is one that's got radar on board. That's the European Space Agency's spacecraft, Mars Express, and others too. So they've built up a topographic map of Mars, and what they've looked at is a region which is called Noctis Labyrinthus, or Labyrinthus, and that name gives it away. It's a labyrinth of features, basically features of the night, I guess, because Noctis is what that means. So it's essentially what you might call a tangled area of geology, the labyrinth of the night, named back in the early days of Mars exploration. So it's easy to see why people have missed this. But when this group of scientists have looked in detail at actually the sort of eastern end of Noctis Labyrinthus, they find basically all the symptomatic structure of a volcano, an arc of mesas, of raised hills, which slope downhill away from the high area, the summit area. And this extends out more than 200 kilometers away from what they actually speculate was the caldera, the volcanic vent, probably once containing a lava lake. We see lava lakes actually on Jupiter's moon Io. We can see their effects, and they are real. So we think that these scientists think that this caldera on this new volcano, or newly discovered volcano, also contained a lava lake. It is being called the Noctis volcano. That's the name that is being given to it because it is so close to the Noctis Labyrinthus region. Fantastic discovery, really extraordinary, isn't it?
Yeah, it is, and it's a big one. It's over 9,000 meters in height and a diameter of 450 kilometers or 280 miles, and to speak American, 29,600 feet. Yeah. From sea level, I suppose, to the summit. Do we call it sea level on Mars?
No, it's got some weird name like the standard datum or something like that.
Yeah.
But yeah, it
wouldn't be that simple.
It's just a standard measurement, and it's funny though because curiously, the northern hemisphere of Mars is generally speaking below that. And we think that the northern hemisphere of Mars once had an ocean in it, and so that datum is probably not far off what would have been sea level then, even though the sea's gone, but the standard is the same. So yes, that's the bottom line. We're measuring it above, and in fact, I think in this case it's probably above the local topography. This volcano, the newly discovered one, and the major other volcanoes that are on Mars, including Olympus Mons, which is on the edge of this area, but there's three other ones, Pavonis Mons and two more. They are in a region that's called the Tharsis Rise, or Tarsus, depending on whether you're correctly pronouncing it or not. It's a high level region, and that the thinking is that this was a sort of bulge caused by magmatic pressure underneath that gave rise to the Tharsis Rise, and the volcanoes have popped out through that. Olympus Mons is on the edge, but Noctis, the new Noctis volcano, is also on that high ground region. So it's fairly, it's a fairly good place to look if you're going to try and find a new volcano. This region where there's a bulge probably caused by magmatic pressure is a good place to look. And the other curious thing about it is that It's at one end of the Valles Marinaris. Is that
yes, I noticed that.
correct?
Yeah, I was going to bring that up. It's quite a fascinating part of the planet. This is around the equatorial regions, I believe. And you've got Valles Marinaris, you've got the new volcano, you've got a string of three to the west, and then Olympus Mons on the edge of that region. It's a really amazing area.
It is, that's right. So Valles Marinaris, the Mariner Valleys, biggest canyons in the solar system as far as we know. But exactly as you've said, they're at one end of it. Look, it makes it look very much as though, back in the times when Mars was warm and wet, water flowed one way or the other, and probably away from the Noctis volcano down towards the low regions in the northern hemisphere of Mars. We're kind of building up a picture of the early geography of Mars. It would have been quite spectacular with the volcanoes and gigantic canyons. What a time to be on Mars with a camera.
And yeah, absolutely. The other interesting thing that's come up in this story is that of glacial ice. And they're already talking about this new discovery being a potential location for a landing zone because of some of the potential resources and what other information might be able to be gained from there.
Right. The kinds of things that you might discover. Yes, they've already identified a possible landing site there. But you're right. And this glacial ice is thought to lie underneath some of the volcanic deposits. So, it probably predates the volcanic activity. That means it's going back almost to the dawn of the solar system, 3.8, 3.9, maybe 4 billion years ago. Really extraordinary discoveries there. Fantastic work by this team of scientists. They've identified all kinds of volcanic features, the sort of stuff that you get, things called rootless cones, which are basically mounds that surround a volcano. There's various lava flows, pyroclastic deposits. That's all the rock and dust that comes out of a volcano. We hear about pyroclastic flows on our own planet, which are very, very dangerous because they've got carbon dioxide as well in their atmosphere. You can't breathe in them. But there's ash, cinders, pumice, all sorts of stuff coming down. And it's all there in this region around the Noctis volcano. So superb piece of work, I think.
Indeed, yes, and worth a read. You can catch that story at the phys.org website. That's the end of this particular program. And don't forget, if you would like to follow us up at any time, jump on our website, spacenuts.io or spacenutspodcast.com. We'd love for you to have a look around. And don't forget, if you want to become a patron, that's the first port of call, our website. And don't forget, if you're a YouTube follower, to hit the subscribe button below, because the more subscribers, the better, as it turns out. I don't really understand it, but all comes down to statistics in the end. And Fred, that brings us to the end. Thank you so much.
It's a pleasure, Andrew. You haven't done the pointing down to the button trick there, but that's where you press. Yes, that's the one. Yeah, very good. I'll see you next time. Maybe at a Q&A session sometime.
Okay. It's very possible, Fred. Thank you. Professor Fred Watson, astronomer at large, part of the team here at Space Nuts, and hoping you can join us on our Q&A episode coming up very, very soon. And thanks to Hugh in the studio for what I do not know, but thanks anyway, and we'll catch you on the next episode of Space Nuts. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast. Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com. This has been another quality podcast production from Bytes.com.